In this section, we're going to talk about transformations of graphs, specifically the shifting, these translations, reflecting, stretching, and compressing. So firstly, let's define what is a transformation. A transformation is a change to a graph based on some various parameters. These can include, as I mentioned, translation, stretching or compressing, or reflections of the graph. Translation, let's begin there. This is a shift of the function. So imagine, if you will, you've got some function, okay? Imagine something that kind of goes up and down, maybe back up, and you want to take this function and just shift all of the points up 1 or 2 units. It's as if you're taking it and you're picking it up and you're dropping it back down, but you're dropping it back down just a little bit higher on your graph. So it keeps the same shape. We're not squeezing anything in, we're not stretching anything out. It keeps the exact same shape. You're just picking it up and then dropping it back down. Well, we could translate something upwards, we could translate the function downwards, and we could translate left and right. To do this, let's look at up and down first. If I want to shift up or down, I'm going to add or subtract some value k to the function. If I add, say, 3 at the very end of the function, well, that's just going to make this go up 3 units. If I subtract 2, this is going to make this go down 2 units. That's pretty intuitive. That makes sense. However, if I look at left and right, this is kind of almost the opposite of what I would imagine, because when I think of a number line, the positive end of the number line, that's toward the right side. The negative end, that's toward the left side. So you would think that if you were to add something to x, so now instead of adding to the end, you're adding inside the parentheses to the x. You would think that if you add to x, you would go to the right, because positive, you're adding, go right. But actually, that makes it go left h units. It's not until you subtract from x that you will go to the right however many units. So if I add 5, my brain goes, okay, well, that's easy. Take the whole graph, move it over to the right 5. But in actuality, you're going to shift the entire thing to the left 5 units. If I subtract 7, you would think you'd go to the left 7 units, but you're going to take that whole graph and you're going to move it to the right 7 units. Dilations. All of these are dilations. These are your stretching and your compression of the graph. So if I multiply at the very front on the outside of the function, if I multiply by a, let's say a is 2, then you're going to take the entire function and imagine it's like dough in your hand. You're going to stretch that entire function vertically up and down by a factor of 2. So in other words, points that you had in the function are going to get doubled to where they currently were. So if you've got a point at 0.2, all of a sudden now it's at 0.4 because you're doubling the distance from the x-axis. And if you do this, say 1 over a, you're going to compress the function. You're going to squeeze it in vertically by a factor of 1 over a. So if I do this as 1/3, everything is going to shrink. It's going to compress to 1/3 of the height that it was before. Then horizontally, now we're not going to do it to the outside. We're going to do this to the x, because we know x, domain, left and right. This is your horizontal. If I multiply x by 4, okay, 4 times x, f of 4 times x, I would think that I'm now stretching this out by a factor of 4 because I'm multiplying x by 4. But actually, I'm compressing it horizontally by a factor of 1 over whatever that is. So this would be 1/4. All of a sudden, I'm now actually squeezing this in left and right to 1/4 of where it was originally. And it's not until I do 1 over b, okay, if I do 1 over 2, 1/2 times x, that's when I'm stretching it by that factor of b. So if I multiply 1 over 2 times x, f of 1 over 2 times x. Now I'm stretching the graph horizontally to double the length. And the last one to talk about here, reflections. If I multiply to the outside negative f of x, this is going to reflect the function vertically. If I multiply by, if I do f of negative x, I plug in not x, but I plug in negative x, this is going to reflect the function horizontally. So a couple things to keep in mind then. As we saw, all the vertical changes happen on the outside of the function, outside of the parentheses, and all of the horizontal changes happen on the inside of the parentheses. However, vertical changes are intuitive. They kind of make sense to us. They act as if, they act how I think they should. But the horizontal changes are opposite of what I think. So what we're going to do, we're going to play around with this in Desmos. So I've got a function here. This is the function f of x equals x to the third minus 3x. So this is it right here. I've got a 0 here and here at negative 1.7320 and positive 1.7320, also 0, 0. And I've got a point at negative 1, 2. That's going to be a maximum here. And I've got a minimum at 1, negative 2. Okay, let's go to my second line here and let's say f of x. You'll notice that this is exactly the same. It covers up my original because Desmos is thinking of this as the same function. So if I take this and I say add 3 at the end, what you'll see is every single point from red to blue got moved up 3 units. So this was at negative 1, 2. If it gets moved up 3 units, it's now at negative 1, 5. This point here was at 1, negative 2, moves up 3 units. It is now at 1, 1. So adding something at the end moves it up. If I subtract, so now let's do minus 1. Now all the points on the red curve here get moved down by 1 unit. So these are vertical translations. Let's do horizontal ones. Now I'm going to add or subtract to the x. So instead of f of x, we'll do f of x plus 1. And I would think that that would move everything to the right 1 unit, but actually moves to the left. So this is kind of a little confusing to see. So I'm going to take the original off. I'm going to put it back on. Take it off. Back on. And we'll see that this was at negative 1, 2, and it moved over to now negative 2, 2. Everything got shifted over to the left 1 unit. And if I, instead of adding, if I subtract, let's do like 4. Now we can see that this point was at negative 1, 2, and I added 4 to the x value to make this 3, 2. Because when I move to the right, okay, it goes from negative 1 to 3. What about these? What about doing this as going to the right and going up? Can I do that? Sure. If I want to move to the right, remember I subtract from x, so let's say minus 4 again. And if I wanted to move up, I could say plus 1. So now all of the points here are moved to the right 4 and up 1 unit. Let's do some stretching and compressing. If I multiply to the outside here 2 times f of x, let's see what happens. Hide the original and let's bring it back in. This point was at negative 1, 2. I'm stretching this vertically by a factor of 2, which means that all of these heights are doubled. So now I'm going from negative 1, 2 to negative 1, 4. This point, positive 1, negative 2, double that is now going to be positive 1, negative 4. You'll notice, though, that the zeros are exactly the same, because if you try to double 0, you still get 0. What if I did 1/2? Okay, so now 1/2, we see that it shrunk. It compressed vertically to 1/2 the height. And if you want to do some horizontal changes, you would do this on the inside of the parentheses. Again, if I do, say, 4, I would think that, oh, everything's going to get multiplied by 4. I'm going to stretch this out. Okay, I'm going to stretch this out. You actually compress this. So we see here, the red here got squeezed in to now 1/4 of the distance. And if I did 1/4, now we see this stretches all of those points. It's going to stretch all of those points to 4 times the distance from 0 that it was before. Lastly, we've got some reflections, but we'll see here, because of the function that negative f of x, this is going to reflect vertically, and f of negative x, this is going to reflect horizontally, but because of the function that we chose, they look pretty similar. If I change the function here, say this is x to the 4th minus 3x now you would see that would be your vertical reflection. And then this would be your horizontal reflection. The last thing to talk about are odd and even functions. Okay. If f of negative x equals f of x, the function is even. Meaning, if you were to plug in not just 3, but you were to plug in -3, and then you get the same thing back as if you plugged in f of positive 3, then the function is even. If, however, you plug in, -3, and you get the opposite of what you would normally get if you plug in f of just positive 3, then the function is odd. So graphically, here's what that looks like. An even function looks like this, where it reflects about the y-axis. So negative xy and xy, okay? Whether you plug in negative x or positive x, you get back the same y. That would be an even function. An odd function reflects about the origin. So this is kind of diagonally. If you would normally get xy, when you plug in negative x, you'll get negative y. Note here, if it is not even and it is not odd, then it's neither, which could still reflect about the x-axis, but that doesn't mean anything to us. Just because it reflects about the x-axis doesn't mean that it's even, doesn't mean that it's odd. It is actually neither. It must reflect either about the y-axis to be even or diagonally here in order to be odd.